Hi everyone, welcome back to Dave's Math Channel. I'm your host David Tear, and this is my sixth lesson in my sub-series on integration, my series on first year calculus. Today I'm going to talk about a very powerful method for integration called substitution. Anyway, let's begin. So this slide kind of shows you how substitution works. If we have some complicated integral that we don't know how to integrate because it's not in one of our tables, what we can do is we can substitute for the variable in the integral, namely x in this case. We can just write x as some function of some other variable. We call it g of t here. I guess t is the variable we're substituting. And if that's the case, then dx is going to be g prime of t dt. And then we can substitute all that back into our integral. And when we're done with that, we get an integral of the form I equals f of g of t times g prime of t dt. That looks kind of messy, but sometimes this integral on the bottom has a form that we can integrate because we know how to do it. It's in one of our tables. So anyway, that's the basic idea. But I think it's better to look at some examples. Once we see a few examples, we'll get a better idea how this works. So anyway, here's the first example. This is a type of integral you see a lot, actually. So now this particular integral isn't in the table that we had. Remember we had 12 integrals of elementary functions. Well, this is one that we didn't have. The integral of x dx over 1 plus x squared. So how would we integrate that? Well, I guess one thing that's kind of tricky about integration by substitution is you have to first figure out a good substitution to use. And sometimes you can just substitute for the whole denominator. If you see a complicated expression somewhere in the integral, a lot of times it's helpful just to substitute that thing, let u be that thing. So in this case, the denominator is 1 plus x squared. That's kind of complicated. Let's just see what happens if we let u equal 1 plus x squared. Well, now we got to calculate the derivative, du, if you like. I mean, you could just say du dx, that's u prime, that's equal to 2x. But it's better to write this in the form du equals 2x dx. And you can always multiply both sides by dx. This quantity du, by the way, is what's called a differential expression. We haven't really talked about those yet, but a differential is just some infinitesimal quantity. In this case, du. You're supposed to think that as the limit of delta u as delta is going to 0. So it's kind of an infinitesimal change in u. So what this equation is saying is if you make an infinitesimal change in u, that's equivalent to 2x times an infinitesimal change in x. Anyway, we haven't talked about differentials yet. I might do that later. But if you don't like that, you can just multiply both sides of the derivative using Leibniz notation by dx. And you get du equals 2x dx. So now we can kind of substitute everything in our integral. Notice that the original integral had x dx in the numerator. Well, 2x dx is du. That means that x dx is du over 2. So the numerator becomes dx over 2. And the denominator, 1 plus x squared, that's just u. So now we have the integral of du over 2u. You can factor out 1/2 because that's just a constant. So we get 1/2 times the integral du over u. But we know how to integrate that. That's just the natural logarithm. Technically, it's the natural logarithm of the absolute value of u. I haven't been writing it this way. But since logarithms of negative numbers aren't defined over the reals, we always use the absolute value. And so we get 1/2 times the natural logarithm, the absolute value of u plus c. But now, since this is an indefinite integral on x, we have to back substitute for x. So since u is 1 plus x squared, we'll get 1/2 ln of 1 plus x squared plus c. Notice that now we no longer need the absolute value because 1 plus x squared is always positive. So that's the answer. That's how, and usually when you do this, you want to differentiate back just to see that if you differentiated 1/2 ln 1 plus x squared, I didn't do it here, you'll find that you do get x over 1 plus x squared, which was what was the original integrand. So anyway, that's how you do the indefinite integral. And now for part B of this example, let's do a definite integral like this. And whenever you have a definite integral, there's two ways you can do it. I mean, one way you could do it is to first solve the indefinite integral. That's the way. That's actually solution 2, and that way is usually actually harder. But let's just do it that way first. So we already got the answer from before. It's 1 half ln 1 plus x squared plus c. Suppose you got that. So now what you could do for solution 2 is you could just substitute 1 half ln 1 plus x squared and use the limits. The lower limit's 0 on x and the upper limit's 1. And then if you do that, you get 1 half times log 2 minus log 1. Well, log 1 is 0, so you're just left with 1 half times ln 2. That's your answer. But let's do it. I prefer solution 1. Usually when we do definite integrals, the nice thing about using substitution with definite integrals is that you don't have to substitute back at the end as long as you change the integrands. As long as the original integrands were integrands, I mean not the integrands, the limits. So the original limit 0, 1, those were limits on x. But then if we make the substitution u equals 1 plus x squared, we have to change our integration limits to limits on u, which in this case are 1 and 2. So now, remember last time before we back substitute, we had the integral of du over u. Now our integration limits are 1 and 2, so we get 1 half ln absolute value of u when we're done solving that integral. And now we don't have to back substitute. We can just substitute the lower limit 1 and the upper limit 2. And when you do that, you get the same thing as on the bottom. You get 1 half times ln 2 minus ln 1, but ln 1 is 0, so you get 1 half ln 2 again. I just prefer doing it that way. I don't know. It's a matter of choice, but I think it's usually less work to not back substitute when you have a definite integral. I guess it depends on the problem. I think there are certain problems where it's hard to compute the integration limits. It may be harder to compute the integration limits on u than back substituting. I think there are examples like that, but usually it's better to just update the integration limits. Anyway, I have a couple more examples. So our second example, let's first evaluate the indefinite integral of cosine 3x. Well, now I think it's pretty obvious the substitution we want to use. We want to let u equal 3x. So now we're going to get du equals 3dx, which means dx equals du over 3. We can pull out 1/3 from the whole integral, and we're just left with the integral of cosine u. Well, we know how to integrate cosine u. That's easy. It's just sine u. So we get 1/3 sine u plus c. And again, since this is an indefinite integral, we have to back substitute. But that's easy in this case because we know that u is 3x. So we're left with 1/3 sine 3x plus c. That's the answer. And let's do a definite integral using the same integrand. Suppose we're integrating this thing from 0 to pi over 6. Well, again, there's two ways you can do this. Let's just, to be different, let's do the top way first. So this is where we don't have to back substitute. So let's just do this step by step. Let's pretend we didn't do the indefinite integral. So now we have to do the same thing we did before. We made the substitution, and you're left with the integral of 1/3 cosine u to u, but now we have to change the integration limits to limits on u, and since u is 3 times x, then we have to multiply these integration limits by 3, so they become 0. For the lower limit's still 0, but the upper limit's now pi over 2. So now we get 1/3 sine u evaluated from u equals 0 to pi over 2. That's just 1/3 times sine pi over 2 minus sine 0. And if you remember your trigonometry, sine of pi over 2 is 1, and sine of 0 is 0, so it's just 1/3 times 1 minus 0, which is just 1/3. So that's, I think, the easy way to do it. The hard way is to, it's not even that much harder in this case, but the hard way is to do the whole integral, indefinite integral first, back substitute, and you get 1/3 sine 3x. Now the limits of integration are, the limits are 0 and pi over 6. So again, you're going to multiply 3 times pi over 6. That gives you pi over 2. You get the same thing as before. And if you work it out, you get 1/3 again. So that's the second example. I guess for these examples, it doesn't make much difference which method you use. Sometimes it does for more complicated integrals, but for the ones I'm giving today, I don't think it really makes any difference. And anyway, let's just do one more example. This was actually an example that was given. I think this was formula 12. So this was actually the integral is in our table, even though we didn't really derive it. I remember I said that the equations 11 and 12 that I went over yesterday, those are ones where you do have to use substitution to derive them. Well, this is one of those, and I want you to see how this works. So suppose that we have the integral of dx over a squared plus x squared, where a is an arbitrary positive real number. We can make the substitution u equals x over a. Why do we want to do that? Because then we have x equals au, and then the whole denominator has a factor of a squared we can pull out. So that's what we're doing. We're letting u equal x over a, and then du is just dx over a. So when you make, that means x equals au and dx is a du. So the numerator becomes a du. And like I said earlier, x squared is a squared u squared. So the denominator becomes a squared plus a squared u squared. And notice that the numerator has a factor of a, and the denominator has a factor of a squared. So a over a squared is just 1 over a. We can pull that out. And when we do that, we're left with the integral du over 1 plus u squared. And you may remember that the derivative of the arctangent of u is just 1 over 1 plus u squared. So this is one. This is an integral we just got for free by virtue of the fundamental theorem of calculus. So that's just the arctangent. So we have 1 over a times the arctangent of u plus some constant c, always an integration constant. And now we back substitute finally. That's easy because we already said u is x over a. So our final answer is 1 over a times the arctangent of x over a plus c. And I believe this was equation 12 in that table I gave you yesterday. Now you see how to do that. And you can do the same trick for the arc sine. In that case, you don't get a factor of 1 over a in front. But for the arctangent, you do. Anyway, and now let's just do an example of a definite integral like this. And here I'm using a specific value of a. I'm using a equals 3. So now we're asked to calculate the integral of dx over 9 plus x squared, x going from 0 to 3. So let's do that. And again, there's 2 ways we can do it. This time I think I'll start with the method. I think I'll just do the method where you don't have to back substitute first, because that's usually easier. So now we're changing the limits of integration. So now we're using the substitution u equals x over 3 in this case. So du equals dx over 3, which means dx is 3 du. And so now we get the integral. And remember, we have to change the limits to limits on u. So now we get the integral from 0 to 1 of 3 du over 9 plus 9u squared. And again, we can simplify things by factoring out 1/3. We get 1/3 times the integral of du over 1 plus u squared, u going from 0 to 1. We already know this integral. It's just the arctangent. So we get 1/3 times the arctangent of u going from 0 to 1. That's just 1/3. I should have written this the arctangent of 1 minus the arctangent of 0, but we know that the arctangent of 0 is 0. So we can just leave that term out. Yeah, and then the arctangent of 1 is pi over 4. You might remember that from trigonometry. It might be easier if you think in terms of degrees. The arctangent, the tangent of 45 degrees is 1, because the slope of a line with a 45-degree angle is 1. And 45 degrees, if you convert that to radians, is pi over 4 radians. Remember, right angle is pi over 2 radians. So you get 1/3 times pi over 4, which is pi over 12. That's doing it the easy way where you don't have to back substitute. But if you wanted to back substitute, it's really not much harder in this case. If you did what we did on the previous slide, remember we had the answer 1 over a times the arctangent of x over a plus c. In this case, a is 3. So you're going to get 1/3 times the arctangent of x over 3. X now going from 0 to 3. Well, again, this is easy. Arctangent of 3 over 3. If you use the upper limit, this is the arctangent of 1. If you plug in 0, you get the arctangent of 0, which, as I said, was 0. So you're off with the same thing. 1/3 times the arctangent of 1, which is 1/3 times pi over 4, pi over 12. So anyway, that's how you do integration by substitution. Very powerful method. I've given you some pretty simple examples here. A lot of times you'll see much more complicated examples. Sometimes it's not so obvious how to substitute. Sometimes you have to do it more than once. Sometimes you have to do it 2 or 3 times. I think I've even done it 4 times, a few times. I mean, the more integrals you'll do, the better you'll get at this. And there's a couple other methods of integration we'll learn later. There's integration by parts and also integration by partial fractions. I'm going to go over both of those later. Anyway, that completes my lesson for today. So thank you for watching. Long live math, and I'll see you guys next time. Bye.